Jai Hind viewers, myself Dr. Sukhwinder Singh, Associate Professor in EN Department from Ajay Kumar Garg Engineering College, Ghaziabad. In this live session, we are going to discuss what are the basic tricks how to solve the numerical problems on DC motor and generator. First of all, let's start with the basic concept regarding the DC shunt motor and DC shunt generator. These are the basic types of DC machine, DC shunt as well as series motor and generator. And after that we have the compound configurations. And most of the times in the examination point of view, the particular numericals are coming from these particular basic types like shunt motor, series motor, shunt generator, series generator. First of all, let's discuss about the DC shunt machine configuration or DC shunt motor. As you can see over here, before solving the numerical problem on the DC shunt motor, first of all you have to see that this will be the terminal voltage. Okay, this will be the terminal voltage, or you can say supply voltage, supply, or here for the DC motor we can write it as a supply voltage supply. And then we have the particular armature circuit. This will be the armature circuit, and this is the DC shunt field. And before solving the DC shunt motor numerical, first of all we have to write the voltage equation. First of all, the first basic equation is the voltage equation, that is the Vs is equals to, this is particularly EB plus Ia into Ra. Okay, this is for the armature circuit. This is the voltage equation, and after that you can also write Vs for the field circuit. The second equation is, the basic equation is that is I field, that is the field current into field resistance. Okay, these two equations we need to know first, and after that we can solve on the basis of these voltage equations what are the requirements in the numericals. In the statement of a numerical, in a particular numerical, the solution is already, or idea to solve that numerical is already in the statement. That's why we have to follow the statement very carefully, and after that we have to go for the solution of this particular numerical side. Next we know that from this particular equation of armature we can solve Ia is equals to Vs minus Eb divided by Ra, like this. And for this particular field circuit we can solve field current for the DC shunt motor like Vs, whatever the Vs supply, divided by Rf. This is all about the basic voltage equations for the DC shunt motor. And now come to the DC shunt generator. In the DC shunt generator we have to see over here, this will be the terminal voltage. Okay, this is the terminal voltage coming from the generator, and you can see here we have the direction of load current, this is the direction of shunt current, and this is the armature current. Now you can see armature current, or you can see the source, this will be the source. Okay, here it is the source part playing, and this will be the source in the case of DC motor. This is the source for DC generator. Okay, and before solving the DC shunt generator based numerical, we must know what is the voltage equation of the DC shunt generator. It should be written like this. We have to cover EB is the source voltage, which is equals to this particular value of Vt, okay, plus Ia into Ra. Okay, this is the terminal voltage, and plus Ia into Ra is the voltage. From that we can obtain Vt like EB, generated voltage. In the case of DC motor we will write this is EB in the case of motor. In the case of generator or DC generator we can write it as Eg. Okay, so we can take this particular let me erase this one, okay, and this one is the generator voltage. Now this is the generator voltage EG. Just a second students. This is the EG, okay, this one is the EG, generated voltage, minus IA into RA, like this. We can write the terminal voltage in this manner, and this one is the generated voltage. EG has to cover up the terminal voltage plus IA into RA drop in this particular equation, and we write VT is equals to EG minus IA into RA. And secondly, if we want to write the equation for field current, then it should be comes out like field current is given by the VT by RF. This is the RF. This is the particular field resistance. So these are the basic voltage equation. The most interesting point in the DC motor and generator we have to take care about that whether it is EB, whether it is EG, we can write like this: E is equals to phi Z N, this NP upon 60 A. And most interesting thing over here is E can be written as K times that is phi into N. This is very important relation in most of the numericals based upon these particular equations. Like we have the flux and we have the speed. In most of the numerical problems there is a variation in the flux as well as in the speed. Sometimes they have in some numericals there will be a case that is the first condition, and we have the flux value and the speed value. Accordingly we have to find the back EMF, either back EMF in the case of motor or generated EMF in the case of DC generator, and after that we have to find the new speed in the second case with the different conditions of flux and particular given value. So we have to solve in such a manner that for every conditions we have to see the variation in the flux and speed. Why there is no variation in this particular other factors? Because these factors K comes under the K, that is the constant, that is Z, that is particular P upon 60 A. This is the constant factor. That's why it will remains constant in both the condition whether we are going to change the flux or speed values. So on the basis of these particular basic equations we can find the solution for the numerical problems. And in the case of DC shunt motor we can have the another relation that torque is directly proportional to phi into IA. So this is the particular relation for the torque in the case of torque equation, and these are the particular values of voltage equations on the DC shunt generator side as well as the field current on the DC shunt generator side. And if we talk about the third point is very important, that is the current equations. In the current equations what we have is we have the total particular armature current is the sum of your line current or load current you can say plus field current. So this is the most important relation for the current also. And in the case of DC shunt motor we have the particular, you can see over here, this is the load current and this is the shunt current, but this is the load current or line current you can say, and this is the armature current. For this particular configuration of motor we have the IL is equals to particularly IA plus IF. You can see the difference in these two, because if we want to solve the armature current for the motor, armature current for the motor comes out to be that is your line current minus your shunt current or field current, okay. You can write like this: IA is equals to this in the case of motor, but in the case of generator that comes out to be IA is equals to IL plus IF. I have already written. So this is the main difference when we are solving the DC shunt motor and generator numericals, you have to follow these relations before solving particular statement. Now let us proceed for the DC series motor. This is for the DC series motor and DC series generator circuit. In the both of these DC series and motor and generator circuit, again the back EMF, or you can say it follows the relation phi Z NP upon 60A, okay, and EG in the case of generator is also phi Z NP upon 60A. There is no change in this particular equation of back EMF and generated EMF in the case of motor and generator for DC series circuit. Okay, now you can see over here in the series circuit of DC series motor, you can see whatever the supply voltage is there and the load current, that current is supposed to be the field current as well as the your armature current. So there is no change in that. Let me erase this one. Okay, now see, in this DC series motor what we have is your load current is equals to the field current as well as the same is known to be the armature current. And if we want to solve the voltage equation for this DC series motor, we have to write like this: Vs is equals to back EMF, this is the back EMF, plus your current is same because this is a series circuit, you can write over here IA like this, and you have to write the particular equation R series plus whatever the resistance of the armature, this will be the equation, and from this equation we can solve the armature current like this: supply voltage minus back EMF divided by R series plus RA. So this is the particular relation for the current, armature current, and we know that torque is directly proportional to flux into IA, and for the initial values of the current when the flux is in the unsaturated condition or non-saturated region, for that particular value we know that flux is directly proportional to IA. For those values of unsaturated regions of flux, we have the torque equation can be modified directly proportional to IA square. So this is the particular equation of torque in the case of DC series motor. And if we talk about the current, as I already told, these are the currents for the DC series motor. And if we talk about the DC series generator, in that case again the circuit is same, but here we have the generator principle or generator output. Then the generated output can be written as in the voltage equation, that is EG comes out to be the terminal voltage, okay, plus your IA into RA plus this IL or IA into R series like this. Then we have the EG is equals to VT plus IA into RA plus this particular R series. So like this we have the voltage equation of DC series generator, supposed to be the one, and then we have the current, whatever the load current, that is supposed to be the armature current in the series circuit, and this is the field current. Okay, then there is no problem in solving this one. Whether we are solving for the armature current, the same current is the load current and same current is the field current. So this is all about the DC series generator. If we want to solve for the particular change in the conditions like particular back EMF or generated EMF, the rest of the factor is constant, that is Z is constant, P is constant, 60 constant, A constant, then we can write it. It also follow the same relation K into phi into N. So this is the very important relation before solving the particular numerical problems. Now come to the first numerical problem. A DC shunt machine connected to a 20 volt supply has an armature resistance including brushes that is 0.12 ohm. and the resistance of the field circuit is 100 ohm. It is already given. The things are given. Find the ratio of the speed as a generator to the speed as a motor. The line current in each case is to be the 80 ampere. As I have already told, when we talk about the particular DC shunt machine, whether it is your line current or load current, then we have to suppose that is to be the IL. IL is, in this case, IL is what? Our 80 ampere. Okay. And in both the condition, whether it is motor or generator, in both the case, this current is to be the 80 ampere. And next thing we have already given, that is including brushes, whatever the armature resistance, that is 0.12 ohm. Let us proceed for this. As we know that E is equals to N into P into phi Z, as I already told. This relations we have already derived, that Pz upon 60 A is constant. Then we have this particular EMF is equals to K into N into phi. This thing we have already derived. Let's fix for the 1 and 2 for generator and motor respectively for this numerical problem. And then we have for generator case, we can consider E1. E1 is equals to K is the constant, N1 is the speed, and phi 1. And similarly for the motor case, we are considering E2 is equals to K into N2 into phi 2, the second case of motor, and first case is for generator. And we have to solve the ratio. What we have to find is find the ratio of the speed as a generator to the speed as a motor. This thing we have to find. We need to calculate the ratio of these two like this. E1 by E2 is equals to N1 by N1 into phi 1 divided by N2 into phi 2. This thing we want to solve for these relations, as we have discussed in the previous slide. Why this particular relation is important when there is a change in the conditions of flux as well as the speed. So we have to take care about what kind of questions is given, what kind of methods we have to apply. That is very important. That is reflected from your particular statement. You have to follow the statement carefully before solving any of the particular problem. Now come to the next. What are the given terms? As I already told, voltage is equals to 250 volt, RA is equals to 0.12 ohm, and RF is equals to 100 ohm. IL is equals to 80 ampere. Now see. Now for generator, IA is equals to IL plus ISH. Okay, where IA is the armature current, IL is the load current, or you can say your line current. Okay, line current, or this is the shunt current or field current. This will be the field current, and this is the armature current. Armature current in the case of DC generator, it is given like this. Okay, now ISH can be calculated as your particular ISH is equals to V by RF, 250 by 100, that is to be 2.5 ampere. Hello students. Yes, ISH comes out to be supply voltage, whatever the supply voltage or the particular your connected voltage to the whole circuit, that is V by RF, 250 by 100, that comes out to be the 2.5 ampere. And the next is IA1. For the particularly in the case of generator, we know that IA, that is IA is equals to IL plus, because this is the source. In the case of generator, the armature circuit is the source. That's why IA is equals to IL plus IF. That's why it comes out to be 82.5 ampere. We have added this 80 ampere line current plus 2.5 is the field current. That's why 82.5. And next we have E1. Now we have to solve the E1. As we know that for this particular numerical, we have to solve the E1 as well as E2 in terms of the particular flux and speed values. And we know that the relation is followed by the equation of EMF is directly is equals to K into phi into N. Let me write again, K is equals to K into phi into N. We are following this equation only for this numerical, and this is E1 is equals to 259.9 after adding this V1 plus IA1 into RA, 250 plus 82.5 and then 0.12. So this is all about how we can solve this particular E1. Then for the next term we have the motor case, and motor case we know that the armature current, as I had discussed in the first slide, that how to solve the DC shunt motor, and then we have the armature current is supposed to be the IL minus I shunt. Okay, now for as per the given values, 80 ampere is the line current, 2.5 is the shunt current, as we have already solved, because both the cases whatever the supply we have, that is the 250 volt. Whether it is DC motor, then the supply voltage is 250 volt. When it is DC generator, shunt generator, then the terminal voltage is 250 volt. That's why we have the I field current is same in both the cases. But now we have the armature current is 77.5 ampere, and accordingly we have the E2. E2 comes out to be the V, means supply voltage minus IA2 into RA, and accordingly what will be the E2? We have E2 is comes out to 240.7 volt as compared to the DC generator case, where we have the more voltage, obvious, because the generator is the source. Next is, after solving this, we have to solve E1 by E2, that is equals to N1 into phi 1 divided by N2 into phi 2. This is the main relation which we have already discussed. Why we are solving this one? Because in the statement it is given, we want the result in the ratio of the speeds. Okay, you can see here, find the ratio of the speed as a generator to the speed as a motor. The line current in each case is anti-ampere. That's why we are solving this for. And we know that in both the cases phi 1 is equals to phi 2. Why this is equals to why these two values are same in the case of motor and generator? Because the field current is same in both the cases. That is the reason why we are taking both the phi 1 and is equals to phi 2. That's why these two terms gonna be cancel out, and we have the ratio of the speed like this. N1 by N2 is equals to E1 by E2 is equals to 259.9 divided by, this is the generated voltage and this one is the motor voltage, and the ratio of the speed comes out to be 1.079. So this is the result we have for this particular numerical. This is the required ratio of the speed in both the cases. So that's all for this particular numerical. And now come to the next numerical. Here we have the 250 volt DC shunt motor on load runs 1000 ampere. Okay, this is the load and it takes 5 ampere. You can suppose this load as a first load current, that is IL1. The total armature DC shunt resistance respectively and field circuit resistance is 0.2 is the armature resistance, 250 ohm is the field resistance. Calculate the speed when the load is put on the motor, and it will take 50 ampere if the armature reaction weakens the field by 3%. Okay, we have to solve the numerical as per the given statement, because firstly it will take 5 ampere, and after loading the motor and it current reaches to 50 ampere, when the current is increased, armature current is going to be increased or load current going to be increased, what will happen? There will be a armature reaction also, and we know that the armature reaction always affect your main field flux, and due to that you can say effect of this particular armature reaction, our main flux going to be reduced in the air gap. In the air gap there will be a weakness of flux, and that is 3%. If we know that this is given as 3%, it comes out to be from 100%, it comes out to be 0.97, okay, of the initial value when we have the previous case or initial condition. That's why in the second case our phi 2 comes out to be, in the second case, or when we are loading the motor, this phi 2 becomes 0.97, okay, 0.97 of phi 1. Phi 1 is the initial condition when the motor is lightly loaded. When the motor is lightly loaded, there is no effect of the armature reaction, or we are neglecting the armature reaction. That's why in the second case, when the motor is heavily loaded, then there will be armature reaction, and it is given in the statement that reaction is of 3%. It will reduce the value of the flux from the initial value when it is lightly loaded. Approximately phi 2 is approaches to the, or in the second case, is 0.97 of phi 1. Phi 1 is the initial condition when there will be a no effect of armature reaction. So let's proceed for this numerical. In this case, let's fix 1 and 2 be the used for the no load and loaded condition. No load, here we are considering like IL1, that is the first case, is 5 ampere when it is 5 ampere, okay. And then let us suppose over here condition respectively E1 divided by E2. Again we have the same condition like N1 into phi 1 divided by N2 into phi 2. Again we have the same case, okay. And we have the, again we have the two conditions, first condition, second condition, and by taking the ratio of these two conditions we are able to solve the numerical or the statement as per the given conditions, okay. Now IL1 is equals to 5 ampere over here. This is the first condition, and the current is very small, 5 ampere near about, and when it is heavily loaded it is approaches to 50 ampere. Now see here, in that case I shunt is given like, because it is a DC shunt motor, whether the your load current or armature current changes with respect to the load, but your field current remains constant because we are dealing with the shunt motor. In the case of shunt motor, we have the voltage supply which remains constant across the armature circuit as well as the field circuit. That's why we have shunt current is supposed to be 250 divided by whatever the field resistance we have, that is 250, it comes out to be 1 ampere, okay. Now we know that the supply voltage is this, shunt resistance is this, armature resistance is 0.2. Now come to the next part. As we have discussed in the first slide, as I have given the statements or written the particular relations how to solve. In the case of DC shunt motor, as I already discussed, IA1 comes out to be the load current minus shunt current, okay. And then from that particular relation we just putting the value. If we are able to understand the main concept behind the DC shunt motor as well as DC shunt generator, after that in the numerical we have just need to put the values, then we will get our answers, then there will be no problem at all, okay. The main concern is you have to understand each and every relation very carefully, okay, whether you are dealing with the motor case or generator case. In this motor case, I load current, that is the line current minus shunt, we have the 4 ampere is the armature current for the lightly loaded condition or first condition, and E1 comes out to be V1 minus IA1 into RA, okay, like that. Then we have 250 minus 4 into 0.2, that is the relation, because this is the 250 volt supply and armature current and the armature resistance. Then E1 comes out to be 249.2. For the second case, IL2 is equals to 50 ampere. Now we have put the load on the shaft of the motor and its current increased to the 50 ampere. But we have to solve what will be the armature current for this case. Let us see. For the armature current, when we put this load current as a 50 ampere, shunt current remains constant. It does not change whether you are putting a heavy load on the machine or light load on the machine, because it is a shunt motor. In the shunt motor case, this current remains same. As we put the values 50 minus 1, it comes out to be the 49 ampere like this. And then we have the E2. E2 comes out to be V minus I2 into RA, that is 250 minus 49. This is the condition into 0.2, that is the armature resistance, and we will get E2 is equals to 240.2 volt. Okay, like this. And then as we have to follow this particular relation, E1 by E2, N1 into Phi1 divided by N2 into Phi2, from this particular relation we are able to solve for this condition, but we have stuck over here, because now for the flux in the statement another point is given. In the previous statement there is no problem because phi 1 is equals to phi 2. No such condition is written like armature reaction weakens the flux. Okay, that is not mentioned in the previous numerical, but here it is mentioned that now the flux is reduced by 3%. That's why in this second case phi 2 becomes equals to 0.97 of phi 1. When we put this value over here, then we have this phi 2 is equals to this, and then we have E1 by E2 ratio comes out to be like this, and then this is N1. N1 is given already in the numerical, and when we put this value, N2 is calculated like 993.69 rpm. So this is the answer for this. This is the required speed of the motor for the case 2. Okay, when it is heavily loaded, 50 ampere current is going on, and then the current speed is reduced from the lightly loaded condition to this 50 ampere current condition, that is 993. This is the reduction in the speed of the DC shunt motor as per the given conditions of 3% armature reaction we have counted over here, and in the previous case the flux is same. Now come to the next numerical, a 460 volt series motor. Now we have the motor is changed, now we have the series motor, and it is running at 500 rpm taking a current of 40 ampere. This is the current condition already loaded and it is taking this much of current. Calculate the speed and the percentage change in the torque if the load is reduced so that the motor is taking. Now we are going to reduce the load on the shaft of DC series motor, and the current is also reduced up to 30 ampere, and we have to solve for these two things: percentage change in the torque, okay, if the load reduced to the motor, this total resistance of the armature, as well as we have to solve the speed also. This is the speed and change in the torque. Okay, the resistance of the armature and field circuit is 0.8 ohm. Assume the flux and field current to be proportional. Assume the flux and field current to be proportional, because in this case we have to go for the condition when there is a unsaturated you can say flux is there. We are not following you can say going towards the region of saturated condition, we are in the unsaturated condition. Now see here how to solve it. Assume this fix for 40 ampere current, and the second one is 30 ampere current. There are two load conditions we have. Okay, then what we have to do is, given V1 is equals to V2, in both the cases it is same, but N1 is already given 500 rpm and IA1 is given 40 ampere. This is the armature current. Okay, and IA2 is 30 ampere as per the statement. And in the case of DC series motor, as I already told in the previous slide at the starting point, when we are discussing about the relationship of for DC series and DC series motor and generator case, I have already mentioned that resistance of armature and R series both are connected in series in a series circuit. That's why this RA plus R shunt is series is equals to 0.8 ohm. Okay, means this is not a shunt, this is for the field circuit, and the total resistance is 0.8 ohm. And for this case flux is directly proportional to what? Armature current. Okay, now as per the condition given, we have to solve E1 is equals to this supply voltage minus IA1 RA. This is very simple, 460 minus whatever the current is there in the first case, and whatever the total resistance of series circuit, like series circuit means RA is there and your field circuit is there. instead of shunt you can write over field circuit. Okay, then what will we have? E1 comes out to be 428 volt. Okay, like this. And then we have E2 is equals to V minus IA2 into RA, that is 460 minus 30 into 0.8. Okay, and after that, after solving this E2 voltage, we have to come forward for the E2. It comes out to be 436 volt. It is obvious this is going to be increased because we are reducing the armature current. Okay, this is the 40 ampere, this one is the 30. Accordingly, we have E1 and E2, both are the changing, and this is the second condition, this one is the first condition. Now come to the next point. We know that flux is directly proportional to IA, and if we take the ratio phi1 by phi2, I1 by I2, like this. Okay, and then we have E1 by E2 is equals to N1 into phi1, N2 into phi2, and we have this N1 by N2 is equals to IA1 by IA2, like this. We have to put the values in terms of the armature current, because we don't have the particular values of flux in the both the cases. What will be the flux? It is not mentioned at all in the particular numerical statement. What we have to do is we can apply the things, other things, like assume the flux and field current to be proportional. Means it is already given that flux is directly proportional to IA, and we want the value of phi1 by phi2. That's why if we remove this proportionality sign, it comes with the k over on the numerator as well as k on the denominator, which is cancelled out, and it is simple to understand that phi1 by phi2 is given like this, IA1 by I2. And accordingly we put this phi1 by phi2 over here in terms of armature current. Then we will get the values like N2 comes out to be E2 by E1 into N1 into IA1 by I2. Now all the things we have in this case, we have calculated E2, E1 as well as N1 is already given to us, IA1 is already given to us, IA2 is already given to us. Which thing was not given in the numerical? That will be the flux. Okay, and how we can solve for that? We have to have the something which is mentioned in the statement. So please read down the statement very carefully before solving any of the particular task in the given numerical. So accordingly the statement is given. I have changed the things like I got the values of phi1 by phi2 in terms of armature current, and after putting these values we have the result for the speed in the second case, when we are gonna reduce the armature current, or means the load current, so that the armature current is reduced to be 30 ampere. For that case we have calculated the speed in terms of these particular ratios, E2 by E1, N1 is given, flux value we got the flux values in terms of armature current, then we put those values and get the answer. This is the N2 in the second case, that is the required result. Now come to the next statement. In the second case we have to solve the percentage change in the torque. If the load is reduced in the same case, we know that torque is directly proportional to phi into Ia, and in the same case in the second case, because for the series motor flux as per the given condition, flux is directly proportional to Ia in the series case. Before the saturation region, we are operating the machine in the unsaturated region. That's why this flux is directly proportional to Ia, and then the torque comes out to be Ia square. Okay, by following this we have to solve for the tau1, that is torque 1 condition, torque 2 condition. Both the conditions also depends upon the different current values of armature, and then by taking the ratio of these tau2 by tau1, we are gonna get the particular values as per the desired result, that is 30 by 40, you can say whole square, and then we have the 9 by 16 is the ratio, and which can be given as in percentage T1 minus T2 divided by T1. T1 is the initial condition, and accordingly what will be the change we receive, that is just a minute, that is 43.75% is the change in the torque, you can see over here. So this is how we can solve both the conditions from the given statement. All the things most of the times are given in the numerical statement. You have to follow each and every instruction given in the statement very carefully, then you will got the answer. There is no doubt in that. Okay, you can't solve that numerical. You can solve numerical if you follow each and every instruction given in the statement very carefully. Now come to the fourth. You can see over here in the fourth numerical, a shunt generator delivers 50 kilowatt at 250 volt. When running at, it is also given 400 rpm. The armature and field resistance are given 0.02 as well as 50 ohm respectively. These are the values of armature resistance as well as field resistance. And then calculate the speed of the machine when running as a DC shunt motor, taking 50 kilowatt input at 250 volt, and then allow 1 volt brush for the contact drop. Here we have 1 volt is the drop for the contacts of the carbon brushes, and we have to solve when this machine is running as a motor. At the initial condition, what thing is given in the statement? It is running as a DC shunt generator and delivers how much power? 50 kilowatt power it is delivering. At what voltage supply? That is 250 volt. So that is the statement. And then if we gonna start with the solution of this, assuming again fix 1 and 2 be used for the generator and motor respectively, and then we have for the given case number 1 generator case, how we can solve it? P1 power is given for the generator case, voltage is given for the generator, and then N1 is also given, that is 400 rpm. This is the initial conditions are given in the statement, and by following the given statement of field circuit resistance is 50 ohm and voltage of the brushes, carbon brushes, how many carbon brushes are there in the basically in the machine? 2 carbon brushes. That's why we are adding up the voltage drop of 1 volt for 2 carbon brushes. 2 multiplied by 1, that is comes out to be 2 volt, and then 1 volt per carbon brush. So this is the voltage drop of the carbon brushes. Next we have the load current can be solved like this, IL1. In the case of DC generator, how we can solve the load current? That is given by whatever the power is given divided by the voltage supply. That is 250 volt terminal voltage is there in the case of generator. Then just by simply dividing the power with the voltage, we are gonna get the 200 ampere, that is the generator case current, or that is the load current of the generator. Now come to the next. As we know that in the case of shunt generator, we can easily solve for the shunt current. Shunt current is very important. I shunt calculation is most of the time in most of the numericals of shunt machines, you have to solve the shunt current. Okay, that is always from the terminal voltage divided by the field circuit resistance. Okay, and if we are solving the shunt current for the motor case, then Vs, whatever the supply voltage, divided by RSH. So it is very simple to solve, because this will gives you the idea that how you can solve for the armature current. Okay, how to solve the armature current, that can be coming from this particular relation. That is very important. Now come to this, and the armature current can be solved like this. IA1 is equals to IL1 plus I shunt, and it is approximately equals to, can be calculated as IA1 is equals to 205 ampere. So this is the solution of the armature current, because we have already discussed all the things in the relationship PPT, how we can go for the given statement. Okay, and how we have to tackle the currents in the machine, whether it is a generator case or whether it is motor case. Accordingly we have to solve the armature current. Okay, now the generated EMF comes out to be, as I already discussed for this one, that is the terminal voltage plus IA into RA drop Here we are adding the brush drop also. If it is given in the statement, you must have to count the carbon brush voltage drop. Okay, in general terms we neglect this carbon brush drop because it is of very small values, but if it is already mentioned in the statement that 1 volt carbon brush drop is there, then you have to include that carbon brush drop. Then only we are able to solve the actual value of generated EMF. Okay, otherwise you are gonna get the wrong answer. So please care about the carbon brush drop, and accordingly we have the 256.1 volt is the actual generated voltage, and terminal voltage is what, approximately 250 volt. Now come to the next case. For the second case, it is the motor case. Again the power is same, that is the power output from the motor is also 50 kilowatt. Then as we know that the supply voltage or terminal voltage, as both the cases the same machine is now converted into a motor, let us suppose, then the voltage supply is same, 250 volt is given, then only we are getting this 50 kilowatt. And accordingly we have the input line current can be solved like this, that is the total load current. Now it is 200 ampere again, as we have discussed in the generator case. But where is the difference gonna occur? What is the main change in the particular machine of motor? The armature current. Now you can see over here, in the case of motor, again this shunt current is 5 ampere, there is no change. Okay, but where is the change? Armature current is different, okay, as per the generator case, because it is following its own particular relationships of motor, and the armature current is comes out to be the line current minus shunt current, because the now the supply source is given to, or means the supply is given to the motor. Okay, that's why IA2 comes out to be 195 ampere like this. And then for this case we have E2 is equals to V2 minus particular IA into RA. Now we have to subtract the drop because we are dealing with the motor case, and the particular back EMF is calculated like this. Here we have the supply voltage minus IA into, because the relation is going to change as compared to the generator case. In the motor case the relation is this, that's why we have to follow this one all again. And then we have this particular equation like 250 minus 195 into 0.02 in minus 2, and we are gonna get the particular voltage of second case as in the motor, that is equals to 244.1 volt. And then we have the gain ratio of E2 by E1 like N2 into phi 2 divided by N1 into phi 1. And then since the field current is constant, now there is no such kind of condition is mentioned that there is a decrement in particular flux values. So that's why we have to take phi 2 is equals to phi 1, means flux in the second case is equals to flux in the initial case. And then we are going to get the N2 is equals to E2 by E1 N1, that is 400, and just by putting the values we are going to get the speed in the second case is 381.25 rpm, and this is the required speed of the motor. Now if you have any query you can ask me. Thank you for the for attending the session. Any query you can ask me right now. Okay student, thank you so much for watching this video. Thanks.